Welcome to our third module, which is dedicated to quantum factoring. In this lecture, we will discuss the problem of quantum order finding, and in particular, we will show how Shor's algorithm allows us to compute the order of an element mod n. We assume that we have a function that realizes the QFT modulo phi of n. Now, here is the way we're going to organize this lecture. First, we will discuss the problem of finding the order modulo n when we know phi of n. And then we will see how the same circuit allows us to find the order modulo n when phi of n is unknown. Now, phi of n is the cardinality of the group of units mod n. If we know phi of n in considering all the ways that we know how to compute phi of n, these would require the factorization of n. So this is more of an artifact. This first half of the presentation is more of an artifact to show you how Shor's algorithm would work in an ideal case. But of course, finding the order modulo phi of n when phi of n is known usually makes no sense in the context of factoring, because knowing phi of n usually implies that we know the factorization of n, in the sense that we do not know of any other ways to compute phi of n other than factoring n. Now, we assume that we have a quantum Fourier transform modulo phi of n. So that is not a problem as long as phi of n is known. And as I said, this is a bit of an artificial case. Now, we would start by creating the uniform superposition of all elements modulo phi of n. And our input state is this tensored by 1. Now, we first apply the controlled exponentiation by x, okay? So we've seen generic techniques for everything that is efficient classically to turn them into something efficient reversibly. Now, the output of this is simply the same state as our input state, except that the second register contains a to the x mod n for all possible values of x. Now, we can rewrite this because when a has the order r, which has to divide phi of n, a to the x mod n only contains a limited number of values. So you have that a to the 0 mod n, then you have a to the 1 mod n, and then a to the 2 mod n, and then if you continue, only stops at a to the r minus 1 mod n, and then it resets. So a to the r mod n is the same as a to the 0 mod n, and you continue, you have a to the 1 mod n, etc., etc., okay? So what it means is our sum could be rewritten with respect to all the potential values that the second register can take. So those values are going to be a to the b for b equals 0 to r minus 1. And we rewrite this, every term that corresponds to an x such that a to the x mod n is a to the b mod n is an x of this form, okay? So a multiple of r plus b, okay? And now what we do is we measure the second register, okay? So measuring the second register will not learn b, but it will fix the value of b. So every term in the sum that consists in the multiple of b will be kept. And so what we get here is 1 over, so we basically keep a fraction 1 over r of all our terms here. So we have 1 over phi of n divided by r times the sum for z equals 0 to phi of n divided by r minus 1 of our zr plus b for the particular b that was chosen. And of course, you can either discard the third register, the second register, or just write it down. We'll discard it just because, just for the sake of space here. Now we will apply the quantum Fourier transform inverse to continue massaging this state and turn it into a state that will whose measurement allows us to answer the question of the order of A modulo n. Now we need to know the action of the quantum Fourier transform on each individual state. So this is given by x is mapped to the sum or over y of exponential minus 2 pi xy over 5n. So we can apply this this term by term on the previous states, and what we get is 1 over square root phi of n times square root phi of n over r times the double sum first over z, so z equals 0 to phi of n over r minus 1, and then sum over y per the expression of the action of the quantum Fourier transform. So sum from y equals 0 to phi of n minus 1 of exponential minus 2i pi, and then so here our x's are of the form zr plus b, so we have to put zr plus b here times y, okay, and the whole thing in the power divided by phi of n, okay, that was for the power of the inside the exponential, and then times y, okay? So now what we're gonna do is invert the sums, okay? So sum over y instead, because what we want is identify the probability of measuring a particular y. So what we need to do is reorder the sum, and then for each individual y, we want to know what is the complex coefficient that corresponds to that exact y, okay? We don't want them floating around in different parts of the sum. And once we know that, of course, the probability is going to be the square of the complex norm of that number, okay? So let's reorder our sum here. So what we get now is 1, still the normalization factor doesn't change, so 1 over square root phi of n times 1 over square root phi of n divided by r. And now we sum over y from y equals to 0 to phi of n minus 1. And now we sum over the z's. I'm just going to say sum over z here for the sake of space, and now exponential minus 2i pi zr plus b times y divided by phi of n y. Okay, now one thing we could do, and we will do, is extract from the power of the exponential the terms that do not depend on z. So there's a minus 2i pi by, none of that depends on z. So we can rewrite, so we have the sum here, so 1 over square root phi of n, square root phi of n divided by r, and now sum over y, and now we can extract from the second sum the exponential minus 2i pi by divided by phi of n, and now we have a sum over z equals 0 to phi of n divided by r minus 1 of exponential. So what is this value going to be? That's going to be exponential minus 2I pi z r y divided by phi of n, all that times y. So this here is my coefficient, times something that has amplitude 1, so that is not a problem. Now, we can rewrite this as zeta to the n, so let's, zeta to the z. So we're going to say this is zeta to the z, and for what zeta? For zeta equals exponential minus 2I pi y divided by phi of n divided by r. Okay, so we have the sum of the terms of a geometric series here, and so that's going to be a very important aspect of when we need to calculate the probability of measuring certain elements y. So we see in particular that a given zeta depends on y, okay? We could have called it zeta sub y, didn't want to overload those notations. Now, what do we have? So this is our sum here, and what we have now is a geometric series, and depending on the value of y, this sum is going to be very different. So if y is not congruent to 0 modulo phi of n over r, then we can simply write this sum as 1 minus zeta to the power phi of n over r divided by 1 minus zeta, okay? And because of zeta being a phi of n over rth root of unity, then this is simply going to be 0. So that is for our amplitude when we have a y not congruent to 0 mod phi of n over r. But on the other hand, if y is congruent to 0 mod phi of n over r, then each of these individual terms here is equal to 1. And so what it means is we simply have phi of n over r. Okay, so we have very different amplitudes here. So you see that the chances of measuring a y that is not 0 mod phi of n over r is going to be, the probability is going to be exactly 0, okay? And that's one of the main difference with what we're going to see in what follows when we don't have phi of n, and then we'll have to deal with approximate values, in which case we're not exactly going to have 0 here. But here, we're in the perfect case when we know phi of n, which again is artificial, but then we have an exactly 0 probability of measuring a y not congruent to 0 mod phi of n over r. And on the other hand, we maximize the probability of measuring a y that is 0 mod phi of n over r. Now in the following, what we're going to see is what does that mean in terms of solving our factoring problem. So the inverse, then the QFT inverse in the end of our state is going to be given by 1 over square root r times the sum for k equals 0 to r minus 1 of exponential minus 2I pi bk divided by r times the state k phi of n divided by r. Okay, so we have a drastic simplification here, and we know that we are going to measure something of this form. Now, what does this mean? We measure our state of which has the following shape. We know for sure that we will get a y of this form. But does this mean that we get r? Remember, r is our goal here. K, the number k that we get, is unknown, okay? So if it's unknown, you can't simply simplify by k in order to learn r from y equals k phi of n over r. So what you hope is that y over phi of n equals k divided by r. We know that, but for some k that is coprime with r, okay? If they're coprime, then you just simplify as much as you can the fraction, and then you'll learn from the numerator and denominator what exact values k and r have. But if they're not coprime, you're going to lose information about r because some of the factor between k and r, common factors, will cancel out. So the question is really, what are the odds that we get a we get a k over r where k is coprime with r? Well, we know that there are 5 r possible k's that are coprime with r for k between 0 and r minus 1, okay, which are the terms of the sum. So the probability is simply at least 5 r over r, and that is, we know estimates. So phi, the behavior of the function phi, of course, is very elusive, but we have at least pessimistic estimates telling us that that probability is going to be at least 1 over log r, which in turn is at worst 1 over log n, okay? And this is an acceptable probability of success, okay? So here, the takeaway here is that we're not going to succeed all the time, but we have good chances of success when it comes to getting a k over r where k is coprime with r, okay? Now, let's see what happens when we want to factor, so when we do not know phi of n in particular. We still need to find the order r of a modulo n, and we know that from the previous lecture on the elementary number theory component of Shor's algorithm. So we will work with the quantum Fourier transform modulo 2 to the n for some large enough n, okay? And we're going to see later what does it mean to be large enough during the analysis of the complexity of the probability of success. Now, of course, instead of getting an exactly a y such that, getting a y and knowing phi of n and knowing that y divided by phi of n is exactly k over r, what we're going to get here is an approximation. So we're going to get a y such that we will be able to prove that y divided by 2 to the n is close enough to a multiple of 1 over r, okay? Now, what's interesting is that, and what justifies having done everything first, modulo phi of n, is that we were going to keep the structure, the entire structure of the algorithm, just the analysis is going to change slightly, okay? So, we start in the same way. We produce the sum over x so the uniform superposition of x, and then modulos this time to the n, and then we have a second register with 1, and then we apply the controlled exponentiation to produce this a to the x mod n in the second register, okay? So nothing has changed so far, except for the fact that we have replaced phi of n by 2 to the n here. Now, we can rewrite this. This time, the rewriting is going to be slightly more intricate, and the reason why is because the number of terms here that stay within the bounds of the summation depend slightly on the b here in the exponent, okay? So basically, the number of terms is MB, where MB is, well, the number of exponents that fit, so of the form ZR plus B that fit between 0 and 2 to the n, which can be rewritten as this floor of 2 to the n minus B minus 1 divided by R. So now, knowing that, once we measure, and we're keeping for now M sub B as a parameter, then when we measure the second register, then we keep only MB terms. And here we've discarded the second register, measured and discarded. So we learned an A to the B mod n, and then we're left on the first register with the state, and then we have rescaled with only M sub B terms. And again, you do not know exactly what M sub B should be here at this point because it will depend on B. Okay, so we'll keep it as a parameter. So now we apply the quantum Fourier transform again exactly as in the previous case, except that we're working here modulo 2 to the n, and so we obtain the state 1 over square root 2 to the n MB times a double sum first over y, okay, all the y's from 0 to 2 to the n minus 1, and then over z, okay. And then we can rewrite that as sums of powers of zeta. The zeta here is the same as before, except the denominator is no longer phi of n, but 2 to the n. Now, what is the probability of measuring a given y? Well, it's exactly this number, okay, which we can rewrite by fact. So these are the sums of the terms of a geometric series. So we have 1 over zeta to the MB divided by 1 minus zeta, and then you can factor by the appropriate values to obtain this sign, the expression with respect to sines. Okay. Now we can prove, and that's a pessimistic estimate, but we can prove that the probability of measuring a y that is that close to a multiple of 1 over r, okay, in the so with this bound on the closeness is at least mb over 2 to the n times 4 divided by pi square, okay? So far, we do not know exactly what that probability is, and that's because we need to adjust the number of qubits lowercase n, okay, so that 2 to the n is large enough to make that probability meaningful, okay? So that we haven't done yet, but otherwise now we've been able to at least lower bound the probability of measuring a y such that y over 2 to the n is close enough to a multiple of 1 over r, which remember is our goal here because we want to recover those multiples of k, those multiples of 1 over r to recover r. So how do we bound that probability of success? Well, we can choose an n such that we have that inequality satisfied. And then we will get an x within those bounds here. So such that x over 2 to the n minus k over r is less than 1 over 2 to the n plus 1. And that will happen. Plus, if you add the constraints that k and r be coprime, you can prove, and that is in the notes, but we're skipping it for this analysis for the presentation. We can prove that that probability is like before, phi of r divided, at least phi of r divided by r, which is an omega of 1 over log n. Okay, so something that we consider is repeating, we would have to repeat log n times, okay? So repeating a quantum algorithm log n times is not going to change the complexity class. If it was polynomial with respect to the size of the inputs, I mean, if one instance is polynomial and then you have to repeat that that calculation log n times, this does not change the complexity class. So that's why people are happy enough with this kind of probability of success. But of course, it won't succeed all the time. Now, k over r, how do you get k over r from x over 2 to the n? Now, remember, x over 2 to the n is close enough to k over r, and we have seen in the previous lecture that it must be, k over r must be a convergence of the continued function expansion of x over 2 to the n. And in particular, we can even prove that it has those special properties of bi. So when we look at convergence of the form ai over bi, okay, and then this is the conversion of this form that satisfies those two properties here. So you can even identify it in the list of convergence. And once you have it, then again, you hope that you were in the case where k is co-prime with r, and you win. So that's it for the order finding part of Shor's algorithm. Now, remember, this was kind of a two-parter where we dealt with what to do with the order of a modulo n in the previous lecture. And here we only focused on how to get to the order of a modulo n through the quantum Fourier transform. Thank you for your attention.